recognize, tag the text. So you tag the text and use the social comments to calculate the sentiment. Sometimes people are not happy with the book. Sometimes people are very happy with the book. Sometimes they are very moderate and give suggestions how to improve. Right? These sentiments have to be captured, and there are various techniques. And topics like interactive visualization for analysis as well as integration, and visualize this data. So any questions? Please post your questions. There's one question, can you share some more information about annealer in terms of its different applications? So, like I mentioned, right, simulated annealing has a goal and most of the time you need to find the right mix. Like you have temperature.
No, sir.
For high temperature to low temperature, there's need to tune the same parameter by changing the mix and increasing the goal or decreasing the goal, right? So in real world, it might be something like this, right? The goal is to find out this particular peak. So in practical example, the challenge is to find out these particular peaks right, and identify which is optimal for this particular goal. And remember, very key is these solutions have to be feasible, right? It has to, what you call, meet the requirements in real world. So having said that, now let's look at some of the practical examples. So we looked at portfolio management, right? Stock market. Now let's look at transportation problem. So you'll be surprised sometimes how transportation is a big problem for logistics, especially where you have multiple cities, right? So let me present some of the challenges in the transportation so that you can start appreciating the complexity of the problem first and how simulate annealing will really help. So you have various cities, right? City 1, Hyderabad. Mumbai.
हॅलो हा सर मी करू का संध्याकाळी तुम्हाला एका लेक्चरमध्ये
City 3, Chennai. Let's put the not just North India and West India, like Delhi. Right? You might have distribution centers in each of those and also a hub, let's say at Kolkata. So most of the logistics companies have challenged in picking up from all these cities and dropping off to all these cities. So when I say this sentence looks very simple, but a truck starts from, let's say, Hyderabad, right? Now, it start picking up the contents, then start going to Chennai first, right? Then after that goes to Calcutta, then again drops off. It's a hub, right? Pick up the goods. Here, drop off and pickups, and then go to Delhi, right? Now within here from Hyderabad, I can have drop-offs to Delhi also. I can have drop-offs to Chennai. I can have drop-offs to Mumbai. So we need to represent this first in kind of like a mix or a linear equation and have a goal, right? What is the goal? To reduce the number of trips, right? Identify the best path which optimizes the pickups and drops. Now coming back to simulate annealing, clearly you need to identify the peaks where the right mix of the itinerary works for overall goal, right? And there are other challenges. I can complicate this problem further, not just the itinerary, but also the mix of goods which can be packed in a truck. For example, there are two items or two products which should not be together, right? For a classic example, they give these tomatoes, which have very less expiry, plus other food goods, right? Like tomatoes can't be more than for a day within a closed environment and in an uncontrolled environment. Can you have other vegetables in the same container? Answer is no, because once one food item gets spoiled, there's a chance of other food items getting spoiled. Right? This is a classic example people give. Similarly, you can find multiple vertical items which together cannot be there within a container. So a mix can't just be mathematical, it has to be feasible. And also there is time-based, right? How long this product can stay in a truck, right? Can tomatoes move from Hyderabad to Delhi? Probably not. They have to find somewhere from nearby Simla or Kashmir or Kanpur, or Ghaziabad, right? So that the tomatoes are delivered in lesser time. So that's about transportation. Similarly, the other interesting problem is traffic. I think most of the people are very familiar where they use Google Maps or MSN Maps or maps they're comfortable with. Now, what is the challenge here? You want to go from Hyderabad to Delhi or Hyderabad to Secunderabad or nearest place or Hyderabad to Vijayawada, right? And you want to start early and then come back early. Or you have only 4 or 5 hours that can be high traffic time and you want to optimize the route. So what is the challenge here? What is the goal here? I want to go and come back in lesser time. Now, what is the mix over here? The routes. How do you identify the route and itinerary? Now, what are the peaks? There will be multiple routes. If you go by, for example, from Gachibowli through the highway, right, national highway, obviously it will be faster. But let's say it's a traffic time to reach Gachibowli, right, from Banjaras, Jubilees, and Hyderabad, it will take forever. Similarly, I can give an example in probably not in Nagpur, but Mumbai, right? If you do not start before 9 o'clock, you're gone, right? You can't reach some of the places in Bangalore or Mumbai, right? Just because of traffic. To reach the highway or to reach that what you call loop across Bangalore. So these are some constraints. That's where the feasibility is very important. It's not just identifying the peaks, but like the statement they said, right? You get onto highway, you can easily reach in 1 hour, but how do you get onto highway? So that's where the feasibility comes. So that's the answer to your question. And looks like there's one more question. Student performance classification and recommendation comes under supervised or unsupervised. Can I do this project using support vector machine? So short answer, is yes. It's a classification, and recommendation is also a classification, filtering, collaborative filtering. And can I do this project using SVM? Yes, you can use support vector machine. Yes, you can do. So any other question, feel free to post. So what's next? So the next session will focus on the actual course content, where we focus on deep learning. Before we move on to the next session, we'll take a small break and look at how machine learning is applied in real world. Right? For another 5-10 minutes. So please confirm.
Look at this beautiful framework. Now we've covered
see the video and hear the video.
Each of these steps briefly. We're gonna dive. Look at this beautiful.
Please confirm. Please confirm the chat window if you're able to see.
Yes, sir, it is visible and audible.
Look at this beautiful framework. Now we've covered each of these steps briefly. We're gonna dive into each of them one by one. The first one is problem definition. The question you're trying to answer in the first step is, what problem are we trying to solve? But before we get into different types of machine learning problems, it's important to note, machine learning isn't the solution to every problem. You might think that that's weird being in a machine learning course, but this is an important concept to remember. So when shouldn't you use machine learning? Well, will a simple hand-coded instruction-based system work? Then you should favor the simpler system over the machine learning system. Such as if you wanted to make the favorite chicken dish we used before in an example, if you had the ingredients and you knew the exact steps you had to take to create your favorite chicken dish, it's probably best that you choose a simple system over using machine learning to try and figure the steps out. Other than these kind of scenarios where you know the simple hand-coded instruction-based system already, most of the time you can probably find value using machine learning. Now comes the first step in identifying the problem we're trying to solve as a machine learning problem. We can do this by matching our problem, the one we're working on, it might be a business problem or some other kind of problem, to the main types of machine learning problem. These are supervised learning, unsupervised learning, transfer learning, and reinforcement learning. We're going to be focused on supervised learning, unsupervised learning, and transfer learning. Why? Because these are the most common ones you'll find and you'll come across in practice. And they're the ones when I was a machine learning engineer or when I work on machine learning problems that have proven time and time again to be useful. Supervised learning is called supervised learning because you have data and labels. A machine learning algorithm tries to use the data to predict a label. If it guesses the label wrong, the algorithm corrects itself and tries again. This act of correction is why it's called supervised. It's like if you were trying to guess the steps it took to turn a set of ingredients, the data, into your favorite chicken dish, the label. If you tried once and got it wrong, you'd tell yourself, this was wrong. Maybe next time we'll try something different. A supervised learning algorithm repeats this process over and over and over again, trying to get better. The main types of supervised learning problems are classification and regression. Classification involves predicting if something is one thing or another, such as if you wanted to predict whether or not a patient had heart disease or not based on their medical records, or what type of dog breed was in an image. If there are only two options, it's called binary classification. If there are more than two options, it's called multi-class classification. So trying to predict heart disease or not heart disease would be binary classification because there's only two classes, heart disease or not heart disease. And trying to predict different dog breeds based on photos in images would be multi-class classification because there are many different kinds of dog breeds. Regression problems involve trying to predict a number. You might hear it referred to as a continuous number as well, which just means a number which can go up or down. A classical regression problem is trying to predict the sale price of a house based on things like number of rooms, the area it's in, how many bathrooms it has, or trying to predict how many people will buy a new app based on website visits and clicks. Unsupervised learning has data but no labels. For example, you might have the purchase history of all customers at your store, and your marketing team wants to send out a promotion for next summer. But they know not everyone will be interested in new summer clothes. So they come to you as the in-house data science and machine learning engineer and ask, do you know who's interested in summer clothes? Well, the thing is, you don't either, but you know you can figure it out from the data you have. So you decide to run an algorithm to find patterns in the data and group customers who purchase similar things together. Once it's finished, you notice two groups. One group of customers who purchase only during wintertime, and one group of customers who purchase mostly during summertime. You label them with winter customers and summer customers and send them to your marketing team. And they thank you for saving them sending out thousands of unwanted emails. I'm sure you've probably got some of those kind of emails in your email inbox before. What's important to note here is that you provided the labels. They weren't there to begin with, but the patterns were. And that's what the machine learning algorithm found. And after inspecting the groups, you're the one who saw the commonalities and applied the labels, such as summer or winter. Problems like this are also called clustering, or putting groups of similar examples together. Recommendation problems such as recommending what music someone should listen to based on their previous music choices often start out as unsupervised learning problems like this. Transfer learning leverages what one machine learning model has learned in another machine learning. For example, say you're trying to predict what dog breed appears in a photo. That's a cute dog. That's my Papi 7. And that's Bella in the background there. She's posing. She knows she's on this lecture. You could find an existing model which is learned to decipher different car types and fine-tune it for your task. Now, why is this valuable? Because training a machine learning algorithm, which means letting it find all of the patterns in data, can be a very expensive task. To find patterns in data, a machine learning algorithm has to make millions of calculations. And although computers are very fast at making calculations aren't free. So, instead of learning everything about different photos from scratch, such as what patterns different trees look like, what different shapes are, like the rectangle down here, what grass looks like, the car type model, the machine learning model which has figured out what kind of different cars look like, has already done most of these things. If you've already trained a model, it might have already figured out, okay, these are trees, not cars, these are grass. And so it kind of has an idea of what different patterns look like. Now, you can think of this as being the same as when you write an essay versus writing poetry. Although the writing styles are different, the writing that you do uses the same fundamental principles. So we can take this car model that it identifies different cars and use its foundational patterns and apply it to our dog breed problem. Of course, there's a few more steps involved here, but that's the basic premise of transfer learning. Reinforcement learning involves having a computer program perform some actions within a defined space and rewarding it for doing it well, or punishing it for doing poorly. A good example is teaching a machine learning algorithm to play chess. The chessboard is the defined space, and the actions are moving pieces. And when I say punishment or reward, these things could be as simple as updating a score with +1 if it wins, and -1 if it loses. The machine learning's algorithm's goal could be to maximize the score. So this means if you've done it right, it should learn moves which lead to wins. Reinforcement learning is what was used for DeepMind's AlphaGo to become the best Go, a complicated Chinese board game, far more complicated than chess, player of all time, defeating many Go world champions. And although promising, reinforcement learning has yet to find its way into many practical applications. And since we're focused on building practical solutions, we've decided to focus on the other kinds of learning, such as supervised learning, unsupervised learning, and transfer learning throughout this course. Now you know the major types of learning, you've now got the tools to tackle step 1 in the framework, problem definition, aligning the problem you're trying to solve to a machine learning problem. So for supervised learning, you might say, I know my inputs and outputs, such as I've got patient records, could be the inputs, and the outputs are whether or not the patient has heart disease. Or your inputs could be the parameters of a different house, and the number of rooms, where it's located, how many bathrooms there are, and your outputs are how much the house costs. So that's a regression problem. And for unsupervised learning, you might say, I'm not sure of the outputs, but I do have inputs, such as customer purchases. And you're trying to figure out which customers are most similar to each other. Or for transfer learning, you may think, my problem might be similar to something else. Can I leverage what an existing machine learning model has learned and use it in my own? Now, don't worry if these kinds of learning are sort of going over your head at the moment. We're going to be building a hands-on project for each of these learning types, supervised, unsupervised, and transfer, throughout the course. In the meantime, have a think about some of the problems you face day to day. Could any of them be classified as a machine learning problem? Are you trying to classify whether one thing is something or another? That's a classification problem. Do you ever try to predict what a number might be? That could be a regression problem.
So any questions?
If participant have any question, post your question in chat box. Everybody has to post your question in chat box.
So one of the questions is, I don't understand, sir, how to use AI with machine learning. So let me try to explain, right, how to blend machine learning with AI. So machine learning algorithms, most of the time, will have a model, right? You have training data, testing data, validating data, right? And you use this information you pick the right algorithm or ML technique and you apply. Right? So in between, there are 2 or 3 steps. Right? So first one will be training, second one will be testing, the third one will be validating, and you have the ML technique. So for this to work through AI, like I mentioned yesterday also, the examples we have seen, we need a knowledge base which contains the historical data. We need to have the inference engine which understands if the data is unstructured. Right? Most of the time, data will not be structured. There will be content, there will be images, there will be videos, there will be documents, there will be text coming from files. And let's say you get the information also through a machine learning techniques. You need explainable AI to explain the results. How was this technique applied? Can you explain the outcome, how you reach this particular outcome, a mix or a route or an itinerary or a portfolio? You again need explainable AI. So there are various elements. So we used simulated annealing. So the another technique is simulation. And for what if analysis, you need again simulation. So I hope this answers your question, how to blend AI with machine learning algorithms. It's not just having a model and use some data for training, testing, and validating, and coming out using ML technique to come up with outcomes. Right? It surely give you some output, but we need the AI to really explain how did you arrive at this? Why is this a better solution? Why should I take this decision? Why should I select this portfolio? And most of the time, as a human being, to give an example, like even in Google Maps, we try to see various routes and see why Google has selected this based on lowest traffic or based on whether any accidents or any traffic is stuck or any construction is happening. You try to rationalize the routes, even though one of the route is not a highway, a national highway. Like the example I was giving in Hyderabad scenario, right? You immediately say, oh, okay, maybe we cannot reach highway, right? But that information has to be provided by AI. And machine learning might not just give that information. It learns, uses the data to learn and enrich the model and apply the algorithm, get the result. But somebody has to explain why this is the best one. Why should I take this decision? Why should I select this portfolio? I hope I have answered your question. I think it was from Nikita. Good question. Any other questions before we move forward to the next session? So in another 2 minutes, we're going to get started on AI techniques, where we look at in this FDP program, right, what are the techniques which have to be covered as part of the course. So what are the techniques which we're going to cover in this? Clearly, in the previous section, we did not focus on reinforcement, but the video touched upon, like chess is one of the chess game or chess where we use reinforcement learning. And we look at decision trees, model, how to evaluate models, right? And how to use neural network, how to use NLP, how to use CNN, RNN, LSTM, time series analysis, and multi-class classification. So we have a hard stop at 12:30. So if you have any questions, this is the right time. So looks like there are no. Oh, there's one question. So what is the criteria to select a specific technique for application, let's say diagnosis of medical data set? So in the medical world, so most of the time, the patient comes in with a particular disease or problem, right? And each disease will have symptoms, medicines, and we have a doctor right? The goal of the doctor is to first identify this specific problem. So most of the time in this domain, we'll have medical records. You'll have pathology reports. You have X-ray images, and you have pathology and blood reports and patients' medical records history, right? So if you're going to use AI, right, first you need to identify a knowledge base or a electronic medical records or some data source where you have this information, right? And you use this information, and also you need to have a knowledge base of diseases, symptoms, and medicines. And you blend these two, right? And also you have doctor's prescription. And you start analyzing or using for diagnosis of medical data set. Let's say which medicine was performing well for a specific disease. And there may be disease variants, they may be dependent, it might be depending on patient's age, patient's geography, location, right? Demographics. So let's say you're analyzing it, and let's say you want to use classification, right? Or clustering. The first decision you have to make is whether you need to have, whether you already have the label data or you do not have the label data. So let's say you do not have the label data and it's completely unstructured. You start doing unsupervised learning, right? You take the unlabeled data and start clustering them, putting them in various groups, right? Saying that this particular patient is above 45, like what we are doing for the pandemic, like the vaccination program. We are putting them in various groups, greater than 45, less than 45, right? People who lie between 20 and 45 or 18 and 45. So what the rationale behind that is to divide the patients in multiple groups, identify where the challenge is, identify the symptoms, identify the disease variants, and also identify which vaccinations and medicines are working, right? So that's one technique, right? Let's say you have the label data. Somebody has organized, identified some of these features, identified X-ray images, associated them, saying that this first patient has this particular disease. Now a new image comes in, a new X-ray image comes in, and you want to identify which disease the person has. There you use supervised learning with classification. We have the images, we have the label data saying that this image comes from a patient who has, let's say, cough or cold, who has COVID-19 with a variant before Delta, right? With a variant after Delta, like black fungus, Japan fungus, right? You put various X-ray images, and a new X-ray image comes in. You do the analysis, use classification, and identify the patient's problem based on the X-ray image. I hope I have answered your question. The question was from Deepali Om Prakash. Thank you.
Sir, can I ask you directly?
Yeah, please.
Sir, actually, I wanted to know how to choose a particular algorithm. Means if I consider the, say, thyroid data set, so it is a supervised, I should go for the supervised learning algorithms.
So, like I mentioned, right, in your case, you have thyroid data set.
Yeah.
Do you have the medical records? Do you have the patient's profiles labeled for a particular disease like thyroid?
Yes, sir.
And do you have set of classes or groups in which this labeled data is analyzed or grouped? Like,
Yes,
for
sir.
example, you know the difference between thyroid and non-thyroid within
Yeah,
the data.
like that.
Right. and you have X-ray images or blood reports or
Pathological
some
reports.
pathological reports, vitals
Yeah.
to associate with the thyroid or without the non-thyroid patient.
Yeah. Hyper
Then
or
you use,
hypo.
yeah, then you use classification.
Classification. Okay, so sir, in classification again, I am having multiple choices. So I can choose any of the algorithm.
Yeah, so that's where one of the questions was, can I use support vector machine? Or can I use multi-class classification? Can I use what you call Bayes classification? There are various algorithms.
Okay.
Most of the time, people go for support vector machine.
Yeah, support vector machine, or it is decision tree, naive Bayes.
Yeah, decision tree is another technique which we'll go through in this particular topic.
So there is no differentiation as such in these particular techniques. I can go for any of the technique.
Yeah, the simplest is support vector machine, right? Decision tree and multi-class classification, or other techniques like Bayes classification.
Okay. So sir, my one question is, in many of the papers, they use a deep learning approach or CNN for the diagnosis purpose. But in one of the paper, they mentioned that it is working like a black box. If we add the hidden layers, our actual output is get refined, but what may happen in that particular hidden layers, that is unknown. So if it is unknown, it is risky if we apply that into the medical field.
Right. So when they say black box, is that most of the time people who are using the model to understand, analyze data, they're not aware of the hidden model. But the first, let's say you're going to create the model, right? You're going to add the data, train the data, validate, test the data. You know within the model what is the technique, what is the neural network, what are the layers, what does each layer do? Most of the time, you know, right? We are going to cover that in CNN and RNN and get into the detail. What are the different ways of laying out a convolution neural network? What are those layers? How many layers are there? What do they do? What features do they target? Most of the time we know when we create the model. Right? So when they say black box, is that I have created this model, I have the pre-trained data set, come up with a new data set and you try it out, these are the output results. That's when most of these research journals say that we treat this as a white box, or a black box, and this is a very well enriched model with pre-trained data set, and we are not going to get into detail about this because this is well proven. But let's say you're going to come with a new model or a new neural network with different layers, focusing on different features for each layer, then you will explain about that more like a white box.
Okay.
I hope I answered your question, but let's revisit your question at the end. When we go through CNN and RNN, you'll appreciate the answer.
Okay, sir. Okay, thank you, sir.
So again here, right, we are focusing on deep learning and some of the techniques which are related to the machine learning techniques. So one of the things which is very popular and straightforward is the decision tree, right? And this might simulate how a human being starts looking at a particular problem, comes up with a decision, right? Like for example, the classic example they give, I want to go outside today, and I get up in the morning. And this is before iPhones or mobile phones or even TV came up, right? Everybody had this decision tree in the mind. What is the outlook? They go outside and they start looking at the cloud, the sun is there, look at the ground, has it rained, right? The standard method we use. Nowadays we have iPhone, we look at the weather and predictions and so on. But we immediately step out and see the sky and see the soil, right? See how the wind is and everything, right? Then immediately it's overcast, it's rain, there's wind. It is sunny but humid, right? And then you see the variations, right? Now, what do I do? If it rains and there's a wind and we want to take a umbrella, will the umbrella work? If it's high wind, I need to take a cab to go out, right? And similarly, it is sunny, humid, and what will be my clothing, right? And I'll decide my clothing if I'm good. If it is sunny and humid, I'll probably wear a t-shirt so that I don't sweat. And overcast, right? It's going to rain, or it is cloudy, right? It's not really sunny. It's not really. There's no rain. Then what do I do? Right? It's cloudy, so I'll take the umbrella. Right? It's sunny, and it's getting into. So I'll take a jacket. If needed, I can protect myself from rain also. It goes out of the control. Right? So you see the decision tree before iPhones and TVs and with the prediction. There was a decision tree in our mind, which was very, very simple, right? 3 or 4 combinations, and you pick up the right thing when you step out of your house. The same thing, we take this problem, for example, the stock market or transportation. The decision tree becomes really complicated. It's not as simple as 3 or 4, like outlook and three different parameters, humidity, 2 parameters, wind, 2 parameters. But like, for example, in the stock market or portfolio, you looked at the risk strategy, right? The risk strategy had 4 or 5 variants. Within each risk strategy, if you look at technicals and fundamentals for a particular stock or a company, the number of variants will increase. Right? So that's where the decision tree did not really work out, and various other techniques started evolving. And also there are ensemble methods, right? And if you look at other methods, oversimple the decision tree, like binary decision tree was very popular. Pre-training, train trees, multivariable tree training, overfitting binary trees, bootstrap aggregation, bagging performance, gradient boosting, random forest. These are all variants over a particular decision tree. The other area which I explained yesterday and did not, is the key difference. Let's say you have evaluated a model, you have trained, right? You have characterized, you have solved, you deploy. The next step is evaluation, which is very important in AI. In any typical algorithm, we put the input data, we have training data, we have testing data, we have validating data, you have a model, you train that, and you get the outcome. Most of the time you're happy. But that's not how it works in AI, right? You also evaluate the model, right? Now let's take a step by step and see how evaluation is done. So you design the model first as an architect and you start deploying. As a user, you're more interested in runtime. Like one of the questions the person asked regarding thyroid data set, right? Or in the research journals, they were talking about as a black box. So this is the key difference between architect and a user. The user focuses on runtime model. He does not worry about the design, right? He assumes there is a runtime model. It's a black box for me. Whereas an architect is actually designing the model. And when the new scenario comes in, right, the current model has to perform. And most of the time it may not work because that scenario is not covered within the training data or the test data or the validation data. Now, when the new scenario comes in, there's a feedback loop which needs to go in to the model saying that we need to add this particular scenario. So as the scenario is added, now let's say it comes out with the outcome, we have to use it for predictions, for forecasts, reporting, planning, discovery, optimization, and analysis. Now, where do we have the evaluation? So just before the prediction, most of the time we evaluate the model, look at the model, identify what is the bias, what are the different metrics for the particular model, right? And like the confusion matrix, what we have, we take that to calculate precision, accuracy. So we'll go to one of the examples in the next section. and see how these metrics are calculated. I think reinforcement learning we touched upon in the morning session, so I'll not spend too much time, especially in the video, how machine learning is categorized like supervised, unsupervised, and reinforcement. So in the reinforcement, like they were saying, there's a reward and there's punishment, right? You have the input raw data and you have the state. Based on the state, you decide whether to give reward or punish. What is the best action, right? And you have an agent and you have selection of algorithm and what is the best action. And based on that particular decision, you give the output. Good example is chess. I think you're all familiar that here is the current state. Right? It might be initial first move or middle game move or end game move. Right? And you have the selection of algorithm, and each algorithm will have a set of historical data based on saying that this particular move has higher probability of winning based on number of games won. Might be a simple model which uses the historical data saying that this is the move. The next move, if you make, let's say you move the knight or bishop, right, to A4 or E4, right? Then there's a higher probability based on the previous historical games. And also the strategies recommended. Similarly, as you move to progress in the game, the chess engine will have capability to either reward you or punish you. Let's say you make a wrong move, right? Then it will clearly say, no, you have made a mistake, and this is the reason you have made a mistake, and you're going to lose. It's like a punishment. So let's move on to neural network, which is more interesting, right? Where we get into deep learning. So how did this deep learning evolve? Right? When did it started, and what were the other techniques before deep learning? So initially, if you look at when, right? I mean, you have natural language generation, natural language understanding, and deep learning started off on various other techniques like speech recognition, machine learning platforms, right? AI optimized hardware, virtual agents, text analytics, NLP, robotic process automation, image video analysis. So pretty much all of these started coming up after the deep learning platforms evolved, right? So like any hype curve, right? Deep learning had its own peak, and it went on for 3-4 years, and then now it's kind of saturated, right? And so I would say probably we are somewhere at the equilibrium, and then probably we're going down, right? And that's when most of the applications really come up. And deep learning platforms did not have great success initially. Now it's slowly starting picking up, but very minimal success. But huge success is primarily on machine learning platforms, speech recognition. Like for example, speech like Siri, right? And other voice recognition, speech recognition agents, right, are there in most of the mobile devices. Biometrics or image and video analysis, or RPA, had moderate success. Swarm intelligence, deep learnings had only minimal success, and we are somewhere at the equilibrium stage at this point. So what is deep learning? There are various companies which have started off creating platforms. So social dynamics are a good example they give is the social media, the tweets, retweets popularity, contagiousness, stickiness, and interactivity. The deep networks have also had spectacular success for pedestrian detection. This is another use case where people wanted to know how pedestrians are using the roads, whether the roads are designed. Similarly, another example is image segmentation yielded superhuman performance in traffic sign classification, detecting emotions from photos, like sentimental analysis. Recommendation engine predicts the proxy of interest or collaborative filtering systems. These were initial use cases where deep learning got popular. Let's look at a very simple example, right, where we look at flowers, iris flower data set, and how we use neural network. Let's start with a very simple example where you have input and output, right? An input data, right, can have weights, and you use that particular weight to calculate like sigma wi si, and an output comes out with a step function, right? So in this case, it's a very simple network where you almost have maximum 3 nodes or 5 nodes, like hidden layer, like 5 nodes. Now here you have weightages, you have inputs, and you have output, and there is a function in between which is doing the transformation. This magic function is actually hidden. It's like a black box. So you have a hidden layer which does the transformation, right? So it's a simple feed-forward network. Now let's look at an example and see how this works. Iris is a famous, what you call, data set for at least for machine learning. I don't know how many people have seen iris flowers, but iris flowers are categorized based on class: Setosa, versicolor, virginica, and there are 3 different types. They are classified based on the petals and sepals. So as it's clearly shown here, what are petals, what are sepals. So you have sepal length, sepal width, petal length, petal width, right? You have 4 inputs and 2 hidden layers, hidden nodes, in this one output, right? So the weightages, or the classes, the values for Setosa is 0, versicolor is 0.5, and iris virginica is 1.0. Now you have the initial data set, which is clearly labeled. So this is an example which I was talking about, where iris or Setosa will have sepal length 5.1, sepal width 3.5, petal length 1.4, 0.2. Right? You have the petals and sepals identified, how they are associated with iris. Right? This is where you use algorithms like classification and neural network, where the input layers have 4 nodes, hidden layers have 2 nodes, and output layer 1. And you identify the learning rate using the training data, and you identify the weights which are used to calculate the output. So very good. So many people are very happy, but they have this question saying that Bhagwan is great, and you're talking about flowers. But in real world, how does this work? It's just a simple flower, but my grandmother used to go into a garden, any garden, not her just house garden, look at the flower, identify, oh, this is Setosa, this is versicolor, for different categories, right? There's no petal length, there's no sepal length, right? Just go into the garden and identify that this flower is rose, this flower is jasmine, this flower is some other category. My grandmother used to quickly pick it up based on the smell, based on the feel and the color. So you're telling that this particular algorithm will work in real life, where a garden consists of multiple flowers, and my grandmother used to just take a minute, and your algorithm has to run for 5-10 minutes to identify a flower, right? So this is the question most of the people have, even the best experts and AI experts. How does this work in real world? Can you give a good real world example? So before getting into the real world example, let's take a step back and look at what is neural network, right? So we're going to train this layer first, right? The first layer, and then the second layer, and the third layer, then the fourth layer, finally the last but layer before getting the output, right? That's what happens in the multi-layer neural networks. So before that, let's focus on NLP for a second and see how in real world you use NLP plus image processing and others to make it work. In natural language processing, you apply natural language processing and understanding to monitor the progress of matters, providing lawyers with ready access with firms' prior work product, allowing clients to perform, like automate lead subtraction process, right? Extracting critical information from contracts. So most of the time, the natural language processing looks at what is related, what is similar, what is missing, and what will happen, right? So we're going to blend this NLP with the image processing and create a multi-layer neural network. And you have sentimental analysis, so you need to identify the sentiments, whether this sentiment is positive or negative. And you have different utterances. Yesterday, we looked at the dialogue flow, the intents and training phrases. A simple training phrase like lunch at McDonald's for $34.35 for a client visit can have easily 10 different combinations. I can say lunch at McDonald's. I can say at McDonald's in Seattle for client name. At McDonald's purpose client lunch. right? Lunch at McDonald's during client visit, lunch at McDonald's for a client visit, right? McDonald's expense, spent $34 lunch. I just put date and lunch and amount. And there are different utterances for these particular training phases. So that's the challenge of NLP. Now let's look at a convolution neural network and come back to our training layers and training multiple layers. Now, let's look at a really complicated example where we have genes, where you have gene network, gene expressions, and you have different layers created based on the gene type, right, or gene expressions. Now, let's take a what you call layman's example of analyzing an X-ray for a patient who has a problem. It might have a cough or a cold. We have not identified the disease yet. But basically, we have his X-rays and the patient's profile. And we know roughly the patient's previous history was they have asthma, and we have detected or noted down the patient's information. So that's the background here. So here, the X-ray consists of image pixels. So I went through this yesterday, but for all, we are going to recap. Each pixel has a value, right? That can be based on RGB or some notation for image where you have a color with a code, a value. But you also have grayscale intensity. You take an image, if you have seen the video yesterday, to recap a video, one of the Google person or one of the employees was saying, you take an image, you transform, make it gray, you identify where the whites are, where the gray are, where real density is. Right? So that's about the grayscale density. Next is the color depth. It's not just white and gray or black and gray, but it's about the color depth. You identify the color intensity, how the color changes, how the depth is. Now let's say you correct all this, right, and push this information through different multiple layers, right, and have a rectified linear unit, and you apply convolution and pooling. Now the next slide, this slide which I'm presenting, answers the morning question, saying that there is a black box, it has hidden layers, I don't know what those hidden layers are. The reason is, most of these Keras pre-trained CNNs are black box. For example, VGG16, VGG19, ResNet 15, Inception V3, MobileNet, DenseNet, NASNet, MobileNet V2. But once you pick a particular pre-trained CNN, you want to go down to its detail, it can be a white box where you can see the code, how each layer is laid out. What are the different nodes in the layer? What are the different functions which are there? And you can see the code. Let's pick an example like lung disease analysis. Now here again, the data is very well labeled. You have gender, male, female. What is the X-ray position? Frontal, back, side. And what are the diseases? We looked at atelectasis, cardiomegaly, and these are the X-ray numbers. Edema, effusion, emphysema, fibrosis, hernia, infiltration, mass, and sometimes no finding, around 3,444, right? Now let's say we use CNN, and then we use the various techniques. We train the model and test the model and validate the model, right? Identify whether it is normal or there's an infection, right? And at the end, we evaluate the model. So how do we evaluate the model? So we use various metrics based on the confusion matrix, where you have true positive, false negative, false positive, and you have various metrics calculated for like precision, recall, accuracy. Precision is true positive by actual results. Recall is true positive by predicted. Accuracy is true positive plus true negative divided by total. And similarly, you have actual results and predicted results. Actual results will be true positive plus false positive. Predicted results will be true positive plus false negative, right? So this is what I was referring to about the model evaluation. And these are the results. So let's see how this works. I'm going to share a video. Please confirm if you can see the video and hear the audio also. So let's look at the sample labels. If you look at the sample labels, so the image index and the finding labels which have the disease name. So various diseases like atelectasis and consolidation, the pneumonia, pneumothorax. There are other disease conditions like consolidation, clearly no finding, sometimes fibrosis, like emphysema, infiltration, capture. You see we have around 5,607 labels. And after capturing the image and the disease condition, we have the patient ID, patient age, patient gender, the view position, right? The image. So you can see one of the images just to
तू इथला माऊस कुठे लावला रे पण?
So let's start looking at the images, right? Sample images. So this is one of the X-ray where it's a frontal position. We're going to look at the second one. This is again frontal, more what you call drilled in or zoomed in. So the X-rays are categorized based on image width, image height, pixel spacing. So here is the code. So it's almost like a white box where you have the diseases. These are the sample labels. The Excel sheet had these diseases associated with the X-ray image file name. It also had what you call other parameters like patient age, type, patient gender, so within age and we had various categories. So these are the training labels, validation labels, and test labels. We read the files for training data, validation data, testing data. So here it's probably 60-20-20 ratio of splitting the data. Good news, it is already split. This is the code behind how to train, how to calculate the metrics. Now here I have started the model training. It goes through various epochs. I had only 2 epochs. And at the end, I have calculated precision, recall, and F beta score. So what are these layers? So here in the code, right, you have a layer 1, which is a convolution 2D layer. Right? It uses ReLU, rectangular linear unit, convolution 1. Layer 2 is convolution 2D layer with squash activation, and then reshapes it into different categories. Layer 3 is a capsule layer where the routing algorithm works. Layer 4 is the auxiliary layer to replace each capsule with its length. The last one is the decoder network. So if you look at each step, the model evaluation happens. You look at the laws, you look at the CAPSNet laws, decoder laws, CAPSNet precision, recall, the beta score, binary accuracy. So here we try to look at the CAPSNet, how this particular network is laid out, how the routing algorithm works, and how the model is evaluated. So now we have reached epoch 2, and we're at 72 step out of 106. This is where the metrics are calculated, like calculating position, like true positive divided by predicted positives plus k dot epsilon. Similarly, how F beta score is calculated. So within the, now that we have completed epoch 1 and within epoch 2, we are at 96 steps out of 106 steps. So in the interest of time, I'm just going to fast forward. So 103, 104, 105. So you got the metrics, how the model got evaluated. And it prints out the values. So what we have used is a very basic VGG CNN. Right? When we talk about the convolution neural network results, after coming back from lunch, I think it's 12:37. I'll do a stop here, and then we can regroup around 1:30 or 1:40. Everybody okay at 1:30?
Yes, sir. Okay, sir. Thank you very much. Thank you for the wonderful session.
We'll regroup at 1:40.
We will meet at 1:30 sharp, sir.
Okay, 1:30 sharp.
1:30 sharp for post-lunch session, and then we will have the valedictory function at 3:30.
Okay, thank you.
Okay, okay, thank you.